In this video, we introduce a new type of probability called conditional probability, which assumes that we know the outcome of the underlying probability experiment is in some event B, and then given that additional information, we calculate the probability that the outcome is also in event A. Formally, conditional probability is calculated as follows. We read the probability of A given B is equal to the probability of their intersection divided by the probability of B, the event that we are conditioning on, or in other words, assuming occurs. In the textbook, there are a number of properties related to conditional probability. First, we have the multiplication law, which simply states that the probability of the intersection of two events can be calculated by first computing the conditional probability of one of the events, let's say A, given that the other event, B, occurs, multiplied by the probability of that conditioning event, in this case B. Alternatively, if you just swap the roles of A and B, we can write the probability of the intersection as the conditional probability of B given that A occurs times the probability of A. Now, this law comes immediately from the definition of conditional probability by simply rearranging the terms in our formula for computing conditional probability, because the conditional probability of A given B, for example, is the probability of the intersection divided by the probability of B. So in the multiplication rule, all we're doing is rearranging by multiplying both sides by the probability of B. The next property that involves conditional probability is the law of total probability, which allows us to calculate unconditional probability of any event by conditioning against events in a partition. So first of all, let's talk about what a partition is. Informally, a partition is just a set of events, or a collection of events, that divide up the sample space into disjoint pieces, and those pieces cover the entire sample space. Right, so if B1 through Bn denote the events in the partition, then their union equals the entire sample space S, and that union is disjoint. So given a partition, the law of total probability says we can calculate the probability of any event A by conditioning it against each of those events in the partition, and then adding up all of those conditional probabilities multiplied by the probability of the partitioning events. The law of total probability actually follows from the multiplication rule, since we can write any event A as a disjoint union of its intersections with each event in the partition. Then for the probability of each of those intersections, we just apply the multiplication rule to calculate it using conditional probabilities. This is an extremely useful result because oftentimes when we have a partition of the sample space, conditional probabilities against those events are known for any other event in the sample space. We will see this in an example shortly. But first, the last and perhaps most important property involving conditional probabilities is Bayes' rule. Again, we start with a partition and some event A, but here we need to assume additionally that the probability of this event A is non-zero, because what Bayes' rule gives us is a way of calculating conditional probabilities for any event in the partition against our general event A. And because the probability of A is going to occur in the denominator then, we need it to have non-zero probability so that this fraction is defined. So what Bayes' rule says here is that if we want this conditional probability, the conditional probability of some event in the partition, say B sub j, given that the event A occurs, then to calculate this, we simply reverse that conditioning. So instead of B sub j given A, we calculate the probability of A given B sub j, which as I just alluded to, we will most likely know. And then we multiply by the probability of B sub j, and finally divide that product by the probability of A. Note that the unconditional probability of A in the denominator here will most likely be calculated using the law of total probability. Now let's go through an example where we look at a test for kidney cancer in order to demonstrate applying Bayes' rule. So what we're given about this test is that it correctly detects when a patient has cancer about 90% of the time. And if the patient doesn't have cancer, the test correctly says so 99.9% of the time. We're going to suppose that we know the incidence rate of kidney cancer is 1 in every 10,000 individuals. And what we're interested in finding is the probability that a patient has cancer given that they test positive. Right, so notice here we're going to find a probability given some additional information. So we are looking for a conditional probability, which tips us off that we should think about applying Bayes' rule. And in order to apply Bayes' rule, we need a partition of the sample space. In this case, the sample space consists of all possible patients. When looking for a partition, it's often useful to think about complements. So in this example, we can partition the sample space into patients that have kidney cancer and the complement, those that don't. So we're only going to have 2 events in our partition. Notationally, let's say B1 equals the event that the patient has cancer, and then B2 is simply going to be the complement of B1, right? So B2 is the event that the patient does not have cancer. Then these events form a partition of the sample space because when you take the union of B1 and B2, we get all patients, the entire sample space. And also their intersection is empty, which we know from the definition of complements. But informally, we also know that an individual can't both have kidney cancer and not have kidney cancer simultaneously. It's physically impossible. Okay, let's also say that A denotes the event that the patient tests positive for kidney cancer. So what we're looking for is the conditional probability that the patient has cancer given that they tested positive. In our notation, this is the conditional probability of B1 given A. So we want the conditional probability of one of our partitioning events given some other event. This is exactly the context for which we apply Bayes' rule. And what Bayes' rule will ask us to do is to reverse that conditioning and then divide by the probability of A. So before we actually apply Bayes' rule, we're going to first apply the law of total probability to find the unconditional probability of A. But before we do either of those, let's actually go back to review the information that we are given and translate it into probabilities of the events that we've just defined. So what we're given in the first line here is that the test correctly detects kidney cancer 90% of the time, which means the conditional probability of getting a positive test given that the patient has the kidney cancer is 0.9. The second statement here says that the conditional probability of not getting a positive given that the patient does not have kidney cancer is 0.999. This implies that the conditional probability of getting a positive test when the patient does not have cancer is 1 minus 0.999, or 0.001. Right? We're using the complement rule on conditional probabilities. Now, this requires some proof, which I am going to omit here. But this essentially follows from the fact that conditional probability is still a probability. In other words, it's a probability measure in its own right. And so the properties in the axioms for probability measures hold true. I encourage you to verify this for yourself. Take the formal definition of conditional probability that we started with in this video and go through and verify that it satisfies the axioms of probability. When you do so, fix a event B that you are conditioning on. Okay, finally, the last bit of information we're given is that our incidence rate of kidney cancer is 1 in 10,000. So in other words, we know that the unconditional probability of B1, the probability of a patient having cancer, is 1 divided by 10,000, or 0.0001. And then from that, we can say that the probability of B2, its complement, would be 1 minus 0.001, and this is going to equal 0.9999. Okay, so now that we've summarized all of the information we were provided with, and we have all of the necessary probabilities in order to calculate the probability that we want, and as I also said, before we can apply Bayes' rule, we first need to apply the law of total probability in order to calculate the unconditional probability of A. Let's go ahead and do that. So the formula states that we can take the conditional probability of A given our events in the partition and then multiply by the individual probabilities of those partitioning sets, then sum them up to get the probability of A. So when you plug in the corresponding numbers here and do the calculation, you'll end up getting 0.0010899. And this is the unconditional probability of a randomly selected patient testing positive for kidney cancer. And I'm writing out all of the decimal places because I want to be as exact as possible here, because I'm not done yet. And so I want to carry this to as many digits as possible so that the final answer is as accurate as possible. We don't want any rounding error here. Okay, so now we can apply Bayes' rule and get the probability that we were initially after. Right, the conditional probability of a patient having cancer given that they actually test positive. Okay, so Bayes' rule says flip the conditioning, so instead calculate the probability of a positive test given the patient has cancer multiplied by the probability of that partitioning event, and then divide by the probability of A, getting a positive test. All right, so the conditional probability of A given B1 we saw was 0.9, and we multiply by the probability of B1, which is 0.0001, and then we divide by what we just found to be the probability of A, 0.0010899. And the final answer is approximately 0.08. Okay, so what is this saying? We've gone through the mechanics, we've applied the formulas, we've done the calculations, and the final answer here is 0.08. But what does it mean? Well, what this says is that there's only about an 8% chance that a patient that has a positive test actually has kidney cancer. Right? Just think about that. If these numbers were accurate, which they aren't, I totally made them up, by the way, then this test really wouldn't be that good, because it's saying of all of the patients that test positive, only 8% of them actually have kidney cancer. But let's think about why this test might actually be useful. It could be that it's not very expensive, or it's not very invasive. So it could be a cheap and easy way for a doctor to initially screen for the disease in a patient that comes into their office complaining of symptoms that could be indicative of kidney cancer. For our purposes, what this example demonstrates is the usefulness of Bayes' rule, how powerful and practically useful it is. Even in this simple, totally made-up example, we can see how such a tool is really important in healthcare, and it has countless other applications as well.